Welcome to section 4 of Unit 2, and in this session we'll be looking at calorimetry and the heat capacity. By the end of this session, you should be able to define some terminologies under heat capacity, calculate heat, specific heat capacity, and then the molar heat capacity of substances. And finally, you should be able to state the Hess's law of constant heat summation and use it to calculate enthalpy change. Now basically, this is a calorimeter. We have the various parts of the calorimeter. We will not go much into the structure of the calorimeter, but basically this is where you put your sample. This is your steel bomb. This is the ignition coil that produces the heat. Then we have the heater. So basically it's an isolated system where the heat gain or the heat lost by the sample is gained by the system. So and this is a typical isolated system where there is no heat loss or gain between the sample and that of the surrounding. But then basically we can measure the quantity of heat, or we can measure our temperature, and then we have oxygen supply and all that. So we will not go much into the structure of the calorimeter, but then just know that the calorimeter is an example of an isolated system. Now, the amount of heat transfer during a reaction can be measured experimentally by measuring the heat flow accompanied a reaction at constant pressure with a device called calorimeter. What is a calorimeter? It's just an insulated vessel with a stirrer, a thermometer, and a loose cover. The pressure inside the calorimeter is constant. That is to say that there is no exchange of pressure between the external surroundings and then the system. And also, the temperature measured makes it possible to calculate the enthalpy change during a particular reaction. So, what is heat capacity? When we talk about heat capacity, which is denoted by the symbol capital C, is the amount of heat or energy required to raise the temperature of an object or substance by 1 degree Celsius. Mathematically, heat capacity is represented as C is equal to Q over change in T, which then we can calculate our quantity of heat to be heat capacity multiplied by the change in temperature. Also, we have what we call specific heat capacity. Note the difference between heat capacity and specific heat capacity. Specific heat capacity is denoted by the symbol small c and is the amount of heat required to raise the temperature of 1 gram of a substance by 1 degrees Celsius. So in this case, we know the specific temperature and then the specific amount of substance we actually require to raise by a specific amount of heat. So specific heat capacity is equal to the heat capacity multiplied by the mass times the change in temperature. So in this case, we can equally calculate our quantity of heat, where we can just take the mass multiplied by the heat capacity multiplied by the change in temperature. Now we can also talk about molar heat capacity. Molar heat capacity, which is denoted by capital C subscript M, is the amount of heat required to raise the temperature of 1 mole of a substance by 1 degree Celsius. It is not that different from specific heat capacity, just that in molar heat capacity we are dealing with the moles of the substance instead of the grams of the substance. So it is also denoted by the symbol C subscript M, and to do that we can equally calculate the quantity of heat, and then this is denoted, or the molar heat capacity times the moles times the change in temperature. So instead of mass, as we saw in specific heat capacity, here it is moles. Now, because enthalpy is a state function, the enthalpy change associated with any chemical process depends only on the amount of matter that undergoes change and on the nature of the final state of the product, as well as the initial state of the reactant. So this means that the step or a series of steps, the sum of enthalpy changes associated with the individual steps must be the same as the enthalpy change associated with the one-step process. So for example, When 1.25 grams of iron reacts with sulfur to form um, iron 2 sulfide, 1.24 kilojoule of heat is released. Calculate the enthalpy of the reaction in kilojoule per mole. So the molar mass of iron is 55.85 gram per mole, and I will advise you to do these calculations. However, if you take this third example, what is the specific heat of silicon if it takes 192 joules of heat to raise the temperature of 45 grams of silicon by 6 degrees Celsius? The answer is 0.71 joule per gram degrees Celsius. So you can do the calculation to confirm the answers yourself. Now, we said we'll be looking, our third objective is to look at the Hess's law of constant heat summation. What does the law say? The law states that if a reaction is carried out in a series of steps, enthalpy change for the reaction will be equal to the sum of the enthalpy changes for each step. So in this example, we are required to calculate the enthalpy change for the reaction 2C, that is 2 moles of carbon reacting with 1 mole of hydrogen to give us 2 moles of methane, given the following reactions and their respective equations. So we have these equations, and we are required to calculate the enthalpy change. So basically, we look at the final, or the final equation we are interested in. What is the final equation? We are interested in 2C plus H2 equal to C2H2. So it is our responsibility to rearrange these equations so that we can cancel those that are on opposite sides to get our respective equations. So anytime you are calculating or using the Hess's law to calculate the enthalpy change of a reaction, remember, whatever you do to the equations, does not affect the enthalpy changes. So however, when you multiply with a particular value or a particular factor, then the enthalpy change for that particular reaction is also affected. So if you are multiplying, for instance, if you are multiplying this equation by 2, then the enthalpy change of this reaction is going to be multiplied by 2. If I am dividing it by half or by 2, then the enthalpy change will divide by 2. So note that whatever you do when you multiply the reaction, then the enthalpy change also is affected. When you reverse the equation as well, then the sign of the enthalpy too also changes. So here you realize that we have CH2 plus this 5 divided by 2 oxygen going to give us 2 moles of carbon plus water. So our responsibility is to maintain carbon and hydrogen in the reactant size. So we are going to, in the first reaction A, we are going to reverse that reaction. So if you reverse the reaction, then you are going to have your carbon and your carbon dioxide and water as product, and then your methane and then oxygen as product side. So at the end of the day, we are going to reverse this equation, and then we are going to maintain B and C. When you do that, then we are going to cancel out the unnecessary items such as oxygen. So oxygen will be able to cancel oxygen, and then however you see that in our initial equation we have 2C. So it is our responsibility to make sure that we actually get 2C on our reactant side. So what we are required to do is to multiply this by 2. So all this equation will multiply by 2, and then the value here too will multiply by 2. Also, we are not going to do anything to this equation. So equation 1 or equation A, we are reversing it. Therefore, the sign also changes to positive. So at the end of the day, oxygen and this oxygen, when you reverse the equation, will cancel, as well as this. The water molecule and the water molecule is also going to be cancelled. Carbon dioxide and carbon dioxide will cancel. Then we are left with 2 moles of carbon reacting with 1 mole of hydrogen to give us 1 mole of methane. And when you do that and you add all the energies, then you should get plus 226.73 kilojoule, and that is basically the Hess's law of constant heat summation. So let's take example 2. Water gas is a name for the industrially important mixture of carbon monoxide and hydrogen prepared by passing steam over hot charcoal at 100 degrees Celsius. The equation is represented as this. Now, the hydrogen is then purified and used as a starting material for preparing ammonia. Use the following information to calculate the enthalpy change for the water gas. So in this example, we are supposed to maintain carbon and water as our reactant, carbon monoxide and hydrogen or hydrogen gas as our product. So in our first reaction, we have carbon there, and what we are required to do is to keep we are going to reverse the reaction A, which will give us 2 moles of carbon dioxide, going to give us 2 moles of CO plus oxygen gas. In the second equation, we are going to reverse the equation as well. And if we reverse it, then you realize that it will be difficult to cancel out the common terms. So we keep reaction B as well as the respective value. With respect to reaction C, we are interested in water as a product, so there is a need to reverse the reaction in C. So please try it and then confirm the answer yourself. In this session review, please do it as possible to calculate the heat needed to raise 27.0 grams of water from 10 degrees Celsius to 90 degrees Celsius, and also try as much as possible to find answers to these questions. And please, as a reminder, if you happen to have any question or any suggestion, please do not hesitate to send us email or any form of or through any medium in which we can use to assist you. Thank you, and I hope to see you in the next session.